Hello everyone, my name is Odarike Charles and today I'm going to show you how you can be able to do Fourier Transform and Fast Fourier Transform using Python so that, let's say in a scenario, you have been given a signal, can be able to tell this signal the frequency that are composing this signal. It becomes a difficult problem because you cannot see it with your eyes. You cannot see a frequency of a signal with your eyes. But now, when you change from time domain to frequency domain, now you can get the magnitude of the signal at different frequencies. So I'm going to show you using that. And first, you're going to do the continuous, then you're going to do the discrete. So for the continuous, you're going to have let me import the following libraries so that we can use them to do that. So the first library I'm going to import is the following. Just a moment. The libraries that I'm going to install. One I'm going to install import numpy as np, import simpy as scp, import simpy as sp. I'm going to from simpy import Fourier. Alright, I just import it from there directly. Then I'm going to install the following from simpy. Okay, so I'm going to install import. Let me import matplot lib.pyplot as plt. What else? I'm going to install import simpy.fft, or I can say from that FFT, import FFT. Then for the FFT, then from that I'm going to import sine plots, then warnings, then I can say warnings dot filter warnings. Then I'm going to ignore them and run that cell. Then it says import cannot import name FFT frec. I think there's something here. There's an F here. Yeah, I think everything is okay. So from that, I'm going to import T and F. Then or I can say from simpy.abc import tf. So I'm going to just define a continuous function, and from this continuous function, now we are going to see what kind of frequencies compose in that function. So I'm going to do what you call Fourier transform from that. So to do that, let me just to do that, I'm going to define a function y equals to sp dot. Let's start with something like every side function. Let me start with that a simple function like sp dot exp, then negative a, like let's say is 5, then t, then you multiply it with the unit step function. We call it every side. This is a unit step function. So you see that. So if you plot it, let's say just y, you can see this is just a hex function. Let me just try to, yeah, you can be able to see this just everything is 0 from negative infinity to 0, but now the value now starts to for the you know that a plot of exponential of negative 4t is just a line that runs from negative infinity from infinity to 0. So but now because you are being multiplied by this unit step function, now things changes. Then I'm going to just have the limit, that is the limit, so say limit, have it from negative 2.5 to 2.5. Yeah, so you can see the plot now. So this is the plot of the function. Now we want to see how much of the frequencies are composed in this, at which at how much, like at frequency of 1, how much, at frequency of 2, how much, until we reach at all, because it's a continuous function. So to do the FFT, just simple. What you can just say is, let's say you want to have the y in f, so in frequency domain from time domain. So this is the plot of time domain. Now we have to do the for the frequency domain. So to do that, just SP that, then you type Fourier transform, then the function is y, then you are going to transform from t to f. So you can see this is the plot here, but it's not computing, just displaying, because I've done the Fourier transform from of y from t to f. They call it correctly, yeah. So you see that we need y of f. You see that this is the Fourier transform. And this is true because when you look for the property of yes, like exponential multiplied by integer function, it's always 1 over the the value. Let me look for it. I can type FFT Fourier transform table. Yeah, this table here. I can just wait it to load so that I'll show you. So here is the table. Okay, okay, yeah, here's the table. You can see that the Fourier transform of an exponential multiplied by a unit step function is just like 1 over a plus j2 pi f. But our a here, our a is 4. So 4, then this 2 pi f plus 4, then they are factored through to get that. Then we want to see the plot of that in frequency domain, how the plot looks like. So the plot of the frequency domain can just say sp dot plot, the same then y of f. Then I can restrict the x limit. So let me say from negative 2.5 to 2.5. So I can get, I think it's not displaying as we expect. So it's not displaying. So I want to say, because you see, in this scenario, you have what? We have a complex number, so it cannot plot. So to plot it, I'm going to find it what we call the magnitude. So I'm going to plot the magnitude. So to plot the magnitude, what I'm going to do, just say sp.abs, then I'm going to type in yf. So if I plot the magnitude, now you can see. So you can see at frequency 0, we are getting a value of 0.25. If I plug in here 0, here 0, it will be like 2 times 2 is equals to 4. So 1 over 4, we get 0.25. At a frequency of 1, if you plug in here 1, you get the values around 0. So this is the plot for the frequency in frequency domain. We can see in time domain it looks like this, then in frequency domain it looks like this. So this is for the continuous function. Let's do another one. We have another property here. I'm going to use another property for and heavy side. We have a rectangular pulse. So I'm going to define a rectangular pulse. So I can say rect pulse. So if you want to define a rectangular pulse, I can use a heavy side. Then I can be able to shift it towards the left by 4. Then I can minus, then toward the right, I can shift to toward the right by 4. So you can see the rect pulse, something that looks like that. But when I plot it, now we can now be able to connect. So if I plot it rect pulse, you can see it. I see the rect pulse, and it has a width of 4. So I can restrict the limit, x limit. Let me say from -5 to 5. So if you plot it, you can see that this is the path from -4 to 4. So I want to do the Fourier transform. I want to get the Fourier transform of this kind of a function, and we see that there's a relationship for the Fourier. You can see the Fourier. The relationship is that we get a T sync pi f tau. Tau sync f by f tau. And tau is the distance, so you can see the value will be like 8 here, right? Because the width is 8, so it'd be like 8 sinc pi f times 8. So that will be our expected value. But now we can do what the Fourier transform. So to do that, you can just say rect pulse in frequency domain, just the same as sp dot Fourier transform. Then you are transforming that rect pulse then from t to f domain. So you can see, let's see what we get from that. We see, as I've said. But now we can be able, we have seen that that's sine 8 pi. This is the same. I'm going to show you why it's the same. So this is the same with 8 sinc pi f times 8. So this, you can be able to transform this into sinc, just a property for it. Okay, so if I plot that, because it doesn't have what we call it doesn't have the complex. If I plot it, I can just get it. So I can say sp dot plot, then I can say sinc. No, I can say rect pass. Then yeah, just like that. So I can get the plot. As you can see, this is the plot, but I want to restrict it so that you can visualize well the plot. So I can have x lim, I say negative 2.5 to 2.5. So you can see this the plot. But I've said this plot is the same for PLT. This plot is the same for what I've said is just something like, let me write it so that I can see it well. I'll say this plot is the same with we know that let me write a markdown here. Let me write a markdown so that I can explain. I've said given sine 8, let me write it like this, frac sine 8 pi f, right, then over pi f. I said this plot, sorry, let me, yeah, I'll say this plot here, no, this function here, the same as with 8 sinc, yeah, and just 8 sinc pi multiplied by f. Let's start with 8 pi, yeah, something this sort. Yeah, this thing, they are the same. This property is the same, right? So if I want to plot it so that I can be able to see, is it the same or not? So I can just have this, what I've just have there. Then I can be able to paste it here. Then I can be able now, instead of this, I'm going to say sp.sync now, right? Then 8 multiplied by sp.pi multiplied by frequency. Then I'm going to multiply it 8, the length of that. So you can see, as you can see, the plots are the same. Yeah, you can see this plot and this plot, they're the same. The only thing is just the implementation. So you can be able to see that if you find the Fourier transform of a rectangular pulse, it gets transformed into a property of sync. If you now do the where you know the time frequency duality, when you do that for sync now, sync, it is in time domain, you get a rectangular pulse in the frequency domain. The only thing that will change is the negative in that thing. I think that's what you can be able to see. From that, now we have done for the continuous. Let's do for the time the discrete now. Let's say you have been given a function that's not continuous, right? It has some discrete. it has some discontinuities, or it's not a function that be able to be visualized well. So I'm going, let me just do the discrete Fourier transform. So to do that, we are going to have these variables. We're going to have the sampling frequency of 1000, then the time, which will be like 1 over sampling frequency, then the number of points, let me use 1000, number of samples, then I can have the time vector, which I can say np dot arrange n, then I multiplied by t, right? So from that, I'm going to have the signals. I'm going to have sine np dot, let me have it on a new line, np dot sine 2 multiplied by np dot pi multiplied by 10 multiplied by t, right? Then plus 0.7 multiplied by np dot sine multiplied by 2 multiplied by np dot pi multiplied by a frequency of 30 multiplied by t. I'm going to add 0.3 multiplied by np dot sine 2 multiplied by np dot pi multiplied by a frequency of 70 multiplied by t. So I can be having such kind of a function. So I can plot this kind of a function and see how it looks like, right? So if I plot it, lt dot plot, I can have the t and the signals, right? You can see this is the signal now, right? I'm going not to do a lot because there's no need to, because just to show. This is now the signal. Now, can you tell what what we, because we know that the frequency is 10, 30, and 70, but when given such kind of a signal, you can't tell the frequencies that are there and the magnitude of those frequencies, and that's what we want to do, to see from this signal what is the magnitude and everything. So if you want to make your plots look very nice, you can have plt.grid, let me say true, let me say line style, let me say okay, I can say alpha 0.1, 0.2, for them to look such kind. Okay, so from that we are going to do the FFT, the fast Fourier transform. For that, let me call it X, capital X. So I just call it FFT, and this FFT, remember this is FFT. We call it here. We called it here FFT. So you can see that when you do that FFT, you just get an array of complex numbers, because when I type this, you can be able to see just an array of complex numbers. Yeah, okay, just an array of complex numbers. So from that, actually, next thing is to find out the frequencies that are in that signal. So we can come to I can call it frequencies, then I can just call it the FFT. Then here we can have the number of samples and the period that we had. Then you can say the magnitude, mag, I can call it mag, is equal to 2 into n multiplied by np dot, the absolute value of that x. So I can have x. So I think I didn't complete here. So you can see the magnitude now is just an array now of not complex numbers but real numbers. So from that we are going to plot. We are going to plot the signal. So to plot the signal, I can just say plt dot let me use this stem because I want to see those stem at each frequency. So I can say frequency, then I can be able to do away with, I want to get the positive frequency only. I can have that. Then I can have the magnitude. Also, I want to get the that are from the just on the right hand only. Okay. Then I can have the base FMT equals that. Yeah. Let me show you. I can be able to do that. I have to disable. Yeah. So you can see that uh, at each frequency, let me have something here so that I don't. So you've got the x of that. Then you have to get the frequency. Then you have to get the magnitude of that, where we take 2 into n. Oh, this you don't have this here. I think now this is where I've had a problem. Yeah, yeah. I was wondering what's wrong. So you can see that uh, these frequencies, the first frequency is at 10, and then at 10 we have a magnitude of 1, as you can see, this one. So we have 1. Then at a frequency of 30, we have the value is 0.7. You can see the value is 0.7. Then at a frequency of 70, the value is equal to 0.3. So to visualize the frequency, well, let us have first frequency at 100, another 200, another 300, so that we can be able to see 12. So let's say 100, another one at 300, the way it is, then another one at uh, 700. You can see the signal that one. Then yeah, so you can see the first one is at 100, another one is at 200. Let us reduce it to 200. Yeah. So you can see the first one is at 100, the value of that. So this is the way you can be able now to do this Fourier transform, visualize the signal, do some analysis on them. So in the next part, you're going to do some fancy and some complicated functions, like doing modulations of function, trying to get from this modulation what kind of frequencies that are appearing. Then you're going to do the filtering, from the filtering using a low pass, transmitting it. Then on the other end, you're going to do the demodulation, now getting into a detector, then doing the band pass and getting the original signal. So this is the next part of this signal, that next section of this that I'll be doing. Thanks for watching. I hope you subscribe to my YouTube channel. Thank you.